At the end of the 19th century, physics stood in a strange and fragile position. From the outside, it looked complete, confident, almost triumphant. Newton's laws had explained motion with astonishing accuracy. Maxwell's equations had unified electricity, magnetism, and light into a single, elegant framework. The universe appeared to be a perfectly tuned machine, governed by continuous laws that flowed smoothly through space and time. Many leading scientists genuinely believed that the great discoveries were over and that the future of physics would consist of refining measurements to ever more decimal places. Yet beneath this calm surface, cracks were forming, and those cracks appeared precisely where physics confronted phenomena that seemed chaotic, noisy, and disorderly. One of the most troubling problems emerged from something deceptively simple: heat. When objects are heated, they emit radiation. This radiation does not come out in a clean, orderly way that classical physics could easily predict. Instead, it spreads across a range of frequencies, creating what is known as a spectrum. Experimentalists measured these spectra with increasing precision, and the data stubbornly refused to agree with theory. Classical physics predicted that as frequency increased, the emitted energy should rise without bound. This result, later called the ultraviolet catastrophe, was not merely wrong, it was absurd. According to the equations, even a warm object should release infinite energy. Reality, of course, did nothing of the sort. This was not a minor technical glitch. It was a direct assault on the idea that nature was continuous and infinitely divisible. Classical physics treated energy like a smooth fluid that could be poured in any amount at any scale. But the experimental results suggested that something fundamental was missing. The more scientists tried to fix the equations by adjusting assumptions, the worse the contradictions became. Order, which physics was supposed to guarantee, collapsed into mathematical chaos. At this point, chaos was not understood as a meaningful concept. It was treated as failure, as evidence that the theory was incomplete or poorly constructed. Noise in measurements was blamed on experimental error. Irregularities were assumed to come from ignorance, not from nature itself. The goal of physics was to strip away apparent randomness and reveal smooth, deterministic laws underneath. Yet the crisis of radiation refused to disappear, and it became impossible to ignore that the disorder might not be accidental. Into this tension stepped Max Planck, a physicist deeply committed to the idea that nature must be lawful and orderly. He was not a revolutionary by instinct. He believed in absolute physical principles and was uncomfortable with probabilistic thinking. For him, the universe was governed by necessity, not chance. Ironically, it was precisely this belief that drove him to confront the chaos head-on instead of dismissing it. Planck approached the radiation problem with a mindset shaped by thermodynamics, the science of energy, heat, and entropy. Thermodynamics had already taught physicists a disturbing lesson: even in systems governed by strict laws, disorder increases, entropy rises. Yet this increase is not lawlessness, it is law of a different kind. Planck understood that disorder could be quantified, measured, and treated as meaningful. Chaos in this context was not the absence of order, but a statistical expression of it. The experimental data on radiation showed a clear pattern, but one that classical equations could not capture. The intensity of radiation rose with frequency, reached a peak, and then declined. There was order in the curve, but not the kind classical physics expected. Planck realized that to match this curve, he would have to abandon one of the most sacred assumptions in physics, that energy changes continuously. The step he took was radical, though he did not initially see it that way. He assumed that energy could only be emitted or absorbed in discrete units, proportional to the frequency of radiation. This assumption was not derived from deeper theory or philosophical conviction. It was an act of desperation, a move made to rescue order from mathematical collapse. In Planck's own words, it was an act of despair. What is crucial to understand is that this act was not motivated by a love of chaos, but by a refusal to accept impossibility. Classical physics had reached a point where its own logic produced nonsense. Infinity appeared where finite values should exist. Prediction failed. Rather than rejecting the data, Planck rejected the assumption that continuity was sacred. In doing so, he transformed chaos from an enemy into a guide. This moment marks the true crisis of classical physics. The crisis was not simply that equations failed, but that the philosophical picture of reality behind them failed as well. The universe was not obliged to behave in a way that matched human intuition. Smoothness, continuity, and determinism were assumptions, not guarantees. The chaotic behavior observed at small scales was not a defect in nature, but a sign that nature operated according to rules unfamiliar to us. The implications were deeply unsettling. If energy came in discrete packets, then the idea of infinitely precise measurement collapsed. There were limits to what could be known, not because instruments were imperfect, but because reality itself imposed boundaries. This was not randomness born of ignorance, but uncertainty built into the structure of the universe. Yet within this uncertainty, there was a deeper form of order. Planck's formula matched the experimental data perfectly. The chaotic mess of radiation spectra suddenly made sense. What appeared random at the macroscopic level emerged from strict constraints at the microscopic level. Chaos was not eliminated, it was explained. This redefinition of chaos is essential. Chaos in this context does not mean absence of law. It means behavior that cannot be predicted by simple, linear rules. It means sensitivity to scale, to conditions, to discrete structures hidden beneath smooth appearances. Classical physics failed not because it was wrong in general, but because it assumed that the same kind of order applied at all scales. The crisis of classical physics, then, was a crisis of overconfidence. It assumed that the universe was transparent to human reasoning, that continuity was fundamental, and that randomness was merely a temporary placeholder for ignorance. Planck's work showed that randomness and order are not opposites. They are complementary descriptions of reality at different levels. This realization reshaped science itself. It taught physicists to take anomalies seriously, to treat contradictions as clues rather than inconveniences. It forced a new humility, an acceptance that the deepest laws of nature might violate common sense while remaining internally consistent and mathematically precise. In retrospect, the chaos at the edge of classical physics was not a sign of failure, but a signal of transformation. The impossible results were not warnings that science had gone too far, but invitations to rethink its foundations. Planck did not defeat chaos by restoring old assumptions. He found order by letting go of them. This is why the crisis matters beyond its historical context. It illustrates a recurring pattern in human knowledge. Systems appear stable until they encounter conditions that expose hidden assumptions. When those assumptions fail, chaos emerges. But chaos is not the end of understanding. It is often the beginning of a deeper, more accurate order, one that demands intellectual courage and philosophical flexibility. The first keynote, the crisis of classical physics at the edge of chaos, is therefore not merely about equations or experiments. It is about the moment when certainty breaks down and understanding must evolve. It is about recognizing that the universe does not conform to our expectations of simplicity, and that true order may lie precisely where intuition says it should not exist. As the implications of this crisis slowly spread, physicists began to realize that the problem was not confined to heat radiation alone. The failure of classical physics at high frequencies was a symptom of a deeper tension between human intuition and the structure of reality. Classical theory had been built on assumptions that felt self-evident: continuity, determinism, and the idea that by knowing enough initial conditions, one could in principle predict everything. These assumptions worked extraordinarily well in everyday experience, which is precisely why their limits went unnoticed for so long. What made the crisis so unsettling was that it appeared at the intersection of order and disorder. On one hand, experiments were remarkably consistent. Different laboratories, different instruments, different materials all produced nearly identical radiation curves. This was not chaos in the sense of randomness or experimental noise. It was structured, repeatable behavior. On the other hand, the equations that were supposed to describe this behavior collapsed into contradictions. Order in observation collided with disorder in theory. This mismatch forced physicists to confront an uncomfortable possibility. Perhaps their mathematical descriptions were not merely incomplete, but fundamentally misaligned with how nature actually works. Classical physics assumed that if something could not be explained smoothly, the fault lay in missing variables or insufficient precision. But the radiation problem suggested that no amount of refinement would fix the issue. The divergence was not a rounding error. It was infinite. The word infinite carried a special kind of alarm. In physics, infinity is often a warning sign rather than a solution. It signals that a model has been pushed beyond its domain of validity. When classical equations predicted infinite energy, they were effectively announcing their own breakdown. This was the edge of chaos in a very precise sense, the boundary where established laws no longer organized reality into something intelligible. The response to this breakdown varied. Some physicists attempted to patch classical theory with increasingly complex assumptions. Others quietly ignored the problem, hoping it would resolve itself. But the data refused to cooperate. The more carefully the radiation spectrum was measured, the clearer it became that the universe was behaving in a way that classical logic could not accommodate. What is often overlooked is how psychologically difficult this moment was. Science is not only a collection of equations, it is also a culture of expectations. The expectation at the time was that nature was fundamentally simple and that simplicity meant continuity. To suggest that energy came in discrete chunks felt artificial, almost crude. It violated the aesthetic sense of smoothness that many physicists associated with truth. Yet chaos has a way of stripping away aesthetic comfort. The edge of chaos is precisely where familiar patterns lose their authority. At this boundary, clinging to intuition becomes a liability rather than a strength. The radiation crisis forced physics into this uncomfortable territory, where elegance had to be sacrificed for coherence. Once the idea of discreteness entered the picture, even tentatively, it began to reshape how chaos itself was understood. The irregularity of radiation was no longer seen as uncontrolled behavior, but as the macroscopic outcome of countless microscopic events constrained by strict rules. Each emission of energy followed a precise condition, but the sheer number of such events produced a smooth curve that looked continuous from afar. Chaos, in other words, was an emergent appearance, not a fundamental lack of order. This shift carried profound philosophical consequences. It suggested that what humans perceive as continuity might be an illusion created by scale. Just as a beach looks smooth from a distance but granular up close, physical processes that seem fluid at large scales may be composed of discrete actions at smaller ones. The crisis of classical physics revealed that order could exist without smoothness, and lawfulness without predictability in the traditional sense. The edge of chaos is also where determinism begins to weaken. Classical physics assumed that given enough information, outcomes were fixed. But the radiation problem hinted that knowing everything about a system's macroscopic state was not enough. The microscopic rules mattered, and those rules did not allow arbitrary subdivision. This introduced a new kind of limitation, one that was not technological but structural. As these ideas settled in, they quietly prepared the ground for a broader transformation. The crisis showed that chaos was not simply ignorance waiting to be eliminated. It was a signal that nature operates on principles that resist complete visualization. Instead of smooth trajectories and continuous flows, reality at its foundation seemed to consist of jumps, thresholds, and limits. This realization altered the scientific attitude toward anomalies. Rather than being treated as nuisances, anomalies became potential gateways to deeper understanding. The ultraviolet catastrophe was not solved by forcing reality to obey old laws, but by allowing the laws themselves to change. In this sense, chaos became creative, It destabilized certainty and made room for a more accurate picture of the universe. Importantly, this did not mean abandoning order or rationality. On the contrary, the new framework that emerged was more constrained, more precise, and more disciplined than classical physics in certain respects. It imposed strict rules on what could and could not happen. Energy exchanges were no longer arbitrary, they were quantized. Possibility itself was structured. The edge of chaos thus became a zone of transition rather than collapse. It was the place where classical descriptions lost coherence, but where a deeper coherence began to emerge. The failure was not of reason, but of assumptions that had gone unexamined for too long. Looking back, the crisis of classical physics teaches a broader lesson about knowledge itself. Systems often appear stable until they encounter conditions that expose their hidden premises. When those premises fail, chaos appears not as destruction but as revelation. The temptation is to retreat to defend familiar frameworks. Progress requires the opposite: the courage to accept that order may exist in forms we have not yet learned to recognize. In this light, the first keynote is not just a historical episode, it is a pattern. Whenever understanding reaches a boundary where predictions explode into contradiction, that boundary marks the edge of chaos. And at that edge, the impossible often signals that a new, deeper order is waiting to be discovered. At the turn of the 20th century, the idea that would later be called quantum did not arrive as a triumphant revelation. It emerged quietly, almost reluctantly, from a mind that did not seek to revolutionize physics, but to preserve it. The second keynote, Planck's radical idea and the birth of the quantum, is best understood not as an act of rebellion, but as an act of intellectual survival. Classical physics had reached a point where its internal logic collapsed under experimental pressure, and the only way forward was to question an assumption so fundamental that few had ever thought to doubt it. At the heart of the crisis lay the assumption of continuity. For centuries, physics had treated energy as something infinitely divisible. You could have half of it, a quarter of it, or an arbitrarily small fraction. This assumption aligned perfectly with everyday experience. Water flows continuously, sound fades gradually, heat spreads smoothly. Mathematics reinforced this view through calculus, which models change as continuous variation. Continuity felt natural, elegant, and inevitable. Yet the radiation problem forced an uncomfortable realization. When Planck attempted to derive the observed radiation spectrum using classical assumptions, every path led to contradiction. No matter how refined the mathematics, the result either diverged to infinity or failed to match the data. The equations were internally consistent, but they described a universe that did not exist. Something had to give. Planck's response was extraordinary precisely because it violated his own philosophical instincts. He assumed that oscillators emitting radiation could only exchange energy in discrete amounts proportional to frequency. Energy was no longer a smooth stream but a staircase. This single assumption fixed the equations instantly. The predicted curve matched experimental results with stunning accuracy. Order returned where chaos had reigned. What makes this moment profound is that Planck did not interpret his assumption as a statement about reality at first. He treated it as a mathematical device, a formal trick to make the equations work. In his mind, the discreteness belonged to the calculation, not necessarily to nature itself. He hoped that a deeper classical explanation would eventually restore continuity, but the universe did not cooperate with that hope. The introduction of discrete energy units did more than solve a technical problem. It changed the meaning of physical explanation. Classical physics explained phenomena by tracing continuous causes and effects through space and time. Planck's assumption broke that chain. Energy exchanges now happened in jumps. There was no intermediate state between one quantum and the next. This was not merely inconvenient, it was conceptually shocking. The birth of the quantum marked the first time physics accepted that nature might impose absolute limits not just on measurement, but on behavior itself. Energy could not be emitted arbitrarily. It followed strict rules that allowed some outcomes and forbade others. Possibility itself became quantized. This idea introduced a new relationship between mathematics and reality. Previously, mathematics had been seen as a descriptive language that mirrored nature's smoothness. With the quantum, mathematics began to reveal structures that intuition resisted. The equations were precise and predictive, yet their implications were deeply counterintuitive. The success of Planck's formula forced physicists to confront a troubling question. If the math works perfectly but defies common sense, which should be trusted? As the idea spread, its radical nature became clearer. If energy was quantized, then light itself behaved in ways that classical wave theory could not fully explain. This opened the door to interpretations that treated light as both wave and particle, a duality that would soon challenge the very categories through which physics understood reality. But at the moment of its birth, the quantum was simply a desperate solution to an impossible problem. The deeper significance of Planck's move lies in how it reframed chaos. The chaotic behavior of radiation was not eliminated by smoothing it out, but by recognizing an underlying discreteness. What looked like disorder emerged from countless tiny, rule-governed events. The quantum did not introduce randomness, it introduced constraint. It limited what could happen, when, and how. This shift also altered the role of probability. In classical physics, probability was often a placeholder for ignorance. If you did not know the exact position or velocity of every particle, you used statistics as a practical shortcut. The quantum suggested something more unsettling: probability might be fundamental. Even with complete knowledge of the system's rules, outcomes could only be predicted statistically. This was not due to lack of information, but due to the structure of reality itself. The birth of the quantum, therefore, marked a turning point in how science understood explanation. Explanation no longer meant tracing a single, continuous causal chain. It meant identifying allowed transitions, constraints, and distributions. The universe was not a clockwork machine unfolding deterministically from initial conditions. It was a system governed by rules that operated at discrete scales, producing patterns that looked smooth only when averaged over vast numbers of events. Planck's reluctance to embrace the philosophical implications of his own idea highlights an important truth about scientific revolutions. They rarely arrive fully formed. They begin as technical fixes, small adjustments made to save coherence. Only later do their deeper meanings become unavoidable. The quantum was born quietly, almost apologetically, but it carried within it a complete reorganization of physical thought. The radical nature of the quantum also lay in what it denied. It denied infinite divisibility. It denied unlimited precision. It denied the idea that nature must align with human intuition. These denials were not philosophical preferences, they were enforced by empirical success. The quantum worked. Classical continuity did not. As the implications unfolded, it became clear that Planck's idea was not an isolated anomaly. It was the first crack in a worldview that had dominated science for centuries. The universe was revealing itself as layered, with different rules applying at different scales. What was continuous at one level was discrete at another. Order was not abolished, it was stratified. This layered order reframed the relationship between chaos and law. Chaos was no longer a sign of missing laws, but of laws operating beyond intuitive reach. The radiation spectrum looked chaotic only because observers were averaging over innumerable quantum events. At the fundamental level, each event obeyed a precise rule. Disorder emerged from order, not from its absence. The birth of the quantum also introduced a new kind of humility into physics. It suggested that some questions might not have deterministic answers, not because humans were ignorant, but because nature did not provide them. This was a radical departure from classical ambition, which aimed, at least in principle, for complete prediction. Planck himself stood uneasily at this threshold. He had opened the door to a new world without fully stepping into it. Others would follow and push the idea far beyond its original context. But the essential act had already occurred. By accepting discreteness, Planck accepted that the universe was structured in a way that defied classical continuity. The second keynote, then, is not merely about a new constant or a clever formula. It is about the moment when physics chose coherence over comfort. Faced with chaos, Planck did not retreat into denial or patchwork fixes. He allowed an impossible idea to stand because it worked. In doing so, he gave birth to the quantum and set science on a path where order would be found not in smoothness, but in limits, jumps, and profound constraint. This is the true radicalism of Planck's idea. It did not promise a simpler universe. It revealed a stricter one. A universe where not everything that can be imagined can happen, and where chaos is often the surface expression of deeper, invisible order. As the quantum idea began to circulate, its true disruptive power slowly came into focus. What initially appeared as a clever mathematical assumption started to behave like a statement about reality itself. The discreteness Planck had introduced refused to remain confined to radiation theory. It surfaced again and again in unrelated phenomena, each time reinforcing the uncomfortable conclusion that nature itself might be quantized at a fundamental level. One of the earliest signs that the quantum was not a mere technical trick came from the study of light interacting with matter. Experiments showed that light could eject electrons from metal surfaces, but only if its frequency exceeded a certain threshold. Increasing intensity did nothing if the frequency was too low, while a weak beam of sufficiently high frequency produced the effect instantly. Classical wave theory had no way to explain this behavior. Energy, if continuous, should accumulate gradually. Instead, the interaction behaved as if energy arrived in indivisible packets, either sufficient or insufficient, with no middle ground. This reinforced the unsettling message already implicit in Planck's work. Nature does not negotiate in continuous shades when operating at its deepest level. It enforces conditions. Either the rule is satisfied, or nothing happens. This all or nothing character clashed violently with the smooth causality that classical physics had relied upon. Yet the experiments were unambiguous. The universe was siding with discreteness. As more physicists engaged with these results, the quantum began to feel less like a workaround and more like a principle. The idea that physical processes occur through permitted transitions rather than continuous flows started to reshape theoretical thinking. Instead of imagining particles sliding smoothly through every possible state, physicists began to think in terms of allowed jumps between specific configurations. The universe was revealing itself as economical, even austere, allowing only certain moves in its underlying game. This perspective transformed the meaning of explanation. In classical physics, to explain something meant to show how it evolved step by step from initial conditions. In the emerging quantum framework, explanation meant identifying the rules that governed which transitions were possible and which were forbidden. The focus shifted from trajectories to constraints. What mattered was not the path taken through every intermediate state, but the structure that determined the outcomes. This shift also altered the emotional landscape of physics. Many scientists felt a profound unease. The quantum did not merely add complexity, it undermined deeply held intuitions about causality and continuity. If energy exchanges happened in jumps, then the notion of smooth cause and effect chains weakened. The universe seemed less like a flowing river and more like a sequence of discrete events stitched together by probability. Yet it was precisely here that a new form of order emerged. The quantum rules were not vague or arbitrary. They were exact. The permitted energy levels of systems could be calculated with astonishing precision. Spectral lines, once mysterious, appeared exactly where the quantum rules predicted they should. The apparent chaos of atomic emissions resolved into beautifully structured patterns. Randomness at the surface concealed rigidity underneath. This tension between unpredictability and strict rule following became one of the defining features of quantum thinking. Individual events could not always be predicted with certainty, but the overall distribution of outcomes followed precise mathematical laws. Order was statistical rather than deterministic. This was not a retreat from rigor, but a redefinition of it. The deeper implication was philosophical as much as physical. The quantum suggested that reality might not be fully describable in terms of classical categories like position, motion, and trajectory. These concepts worked well at large scales, but they blurred at the quantum level. Instead, reality seemed to be structured around relationships, probabilities, and constraints. The question shifted from, "What is the particle doing right now?" to "What outcomes are allowed, and with what likelihood?" This new way of thinking challenged the long-standing belief that uncertainty was merely a reflection of ignorance. In classical physics, if you could not predict something, it was assumed that you simply lacked information. The quantum undermined this assumption. Even with complete knowledge of the system's governing rules, certain outcomes remained inherently unpredictable. Uncertainty was no longer a defect of measurement, it was woven into the fabric of nature. The birth of the quantum also forced scientists to confront the limits of human intuition. The success of the theory demonstrated that nature does not prioritize comprehensibility. It prioritizes consistency. The universe does not care whether its rules feel natural to human minds shaped by macroscopic experience. It only cares that they work. This realization demanded intellectual humility on an unprecedented scale. As the implications spread, resistance was inevitable. Some physicists hoped that the quantum would eventually be absorbed into a deeper classical framework, restoring continuity and determinism. Others embraced the new paradigm more fully, accepting that the universe might be fundamentally discontinuous. The debates were intense, not only because of technical disagreements, but because the quantum threatened to redefine what it meant to understand something at all. What gradually became clear was that the quantum did not destroy order, it relocated it. Order was no longer found in smoothness and predictability, but in constraint and structure. The universe operated according to strict rules that limited what could happen, and within those limits, probability governed outcomes. Chaos, when it appeared, was not lawlessness but the macroscopic expression of countless microscopic events obeying precise conditions. In this sense, the birth of the quantum can be seen as a reconciliation between chaos and order. It showed that apparent randomness does not imply absence of structure. On the contrary, randomness can be the visible consequence of deep, invisible regularities. The radiation spectrum, once a symbol of theoretical failure, became evidence of a hidden architecture underlying physical reality. This realization also reshaped the role of theory itself. Theory was no longer expected to provide a continuous picture that matched intuition at every point. Its role was to provide a framework that reliably connected observations, even if the underlying mechanisms defied visualization. Understanding became less about picturing reality and more about accepting the rules that govern it. The quantum thus marked a turning point in the philosophy of science. It demonstrated that truth does not require comfort, and that coherence does not require familiarity. A theory could be deeply unsettling and yet profoundly correct. The measure of success was not whether it aligned with everyday experience, but whether it organized phenomena into a consistent, predictive structure. Planck's reluctant step into discreteness opened a door that could not be closed. Once the quantum existed, it demanded to be taken seriously. It propagated through physics, reshaping atomic theory, chemistry, and eventually technology itself. But at its core, it remained what it had always been: a response to impossibility. When classical continuity failed, discreteness succeeded. The second keynote, in its full depth, is therefore about more than the introduction of a new constant or concept. It is about a transformation in how humans relate to the unknown. Faced with chaos that could not be smoothed away, physics chose to listen rather than dominate. It accepted that the universe might operate according to rules that feel alien, and that embracing those rules could restore order at a deeper level. In the end, the birth of the quantum stands as a reminder that progress often begins with intellectual discomfort. The ideas that change our understanding of reality are rarely the ones we find intuitive or pleasing. They are the ones that refuse to go away because they work. The quantum worked, and in working, it revealed a universe that is not continuous and gentle, but discrete, constrained, and profoundly ordered beneath its apparent chaos. What appears random to the human eye has often been mistaken for evidence of disorder, but one of the most profound lessons emerging from early quantum theory is that randomness can be a surface phenomenon, a macroscopic illusion generated by deeper, invisible rules. The third keynote, the idea that discreteness is hidden beneath apparent randomness, represents a decisive break from the classical assumption that unpredictability always signals ignorance or lack of control. Instead, it reveals a universe where strict structure operates at scales too small and too fast for intuition to follow directly. Before the quantum revolution, randomness in physics was usually treated as a temporary placeholder. If a system behaved unpredictably, the assumption was that not enough information was available. With better instruments, finer measurements, or more complete equations, the randomness would eventually dissolve into deterministic order. This belief was deeply rooted in classical mechanics, where knowing the exact position and velocity of every particle, at least in principle, allowed complete prediction of the future. Randomness was epistemic, not fundamental. Yet as physicists began to explore atomic and subatomic phenomena, this assumption repeatedly failed. Consider the emission of light from heated objects or excited atoms. Individual emission events occurred at unpredictable times. There was no way to say exactly when a particular atom would emit a photon. To classical intuition, this looked like chaos, irregular, noisy, and uncontrollable. But when large numbers of atoms were observed together, a remarkably stable and precise pattern emerged. Spectral lines appeared at exact frequencies. Intensity distributions followed strict mathematical curves. The randomness of individual events gave rise to reliable, reproducible order at the collective level. This duality was deeply unsettling. How could exact laws emerge from unpredictable events? Classical thinking struggled with this question because it assumed that order must be visible at the level of individual causes. Quantum theory inverted this expectation. It suggested that order might exist not in the timing of individual events, but in the constraints governing which events are allowed to occur at all. The concept of discreteness was central to this shift. Energy levels in atoms were not continuous. They formed distinct steps. An electron could occupy one level or another, but nothing in between. When it transitioned between levels, it did so abruptly, releasing or absorbing a specific quantum of energy. The timing of this transition could not be predicted with certainty, but the amount of energy involved was exact. Randomness governed when something happened, but discreteness governed what could happen. This distinction is crucial. Randomness did not mean arbitrariness. The universe was not making free-form choices. It was following strict rules that limited possibilities sharply. The apparent disorder lay in the sequence of events, not in their structure. At the deepest level, nature was highly disciplined. This realization required a radical rethinking of causality. In classical physics, causes unfold smoothly into effects. In the quantum picture, causes define probabilities. They establish a landscape of allowed outcomes, each with a specific likelihood. The universe does not specify which outcome will occur in a single instance, but it specifies with precision how often each outcome will occur across many instances. This statistical regularity is not a compromise, it is the law itself. Discreteness plays a critical role in making this possible. Because energy, momentum, and other quantities come in fixed units, the range of possible outcomes is inherently limited. This limitation produces structure even when individual events are unpredictable. Without discreteness, randomness would smear outcomes continuously, and sharp patterns would not form. The existence of well-defined spectral lines, stable atomic structures, and consistent chemical behavior depends entirely on the quantized nature of physical properties. This hidden discreteness also explains why macroscopic reality appears smooth and continuous. When enormous numbers of quantum events are averaged together, the underlying steps blur into apparent continuity. Temperature, pressure, and light intensity feel continuous because they are collective measures of countless discrete interactions. The randomness of individual events cancels out statistically, leaving behind stable averages. What humans experience as smooth order is the large-scale shadow of microscopic discreteness. This perspective reframes chaos itself. Chaos is no longer the absence of rules, but the manifestation of too many rule-following events to track individually. The unpredictability of a single atomic decay does not undermine the predictability of half-life measurements across millions of atoms. On the contrary, the stability of half-lives depends on the randomness of individual decays being governed by fixed probabilities. The philosophical implications are profound. They suggest that nature does not privilege the individual event as the primary unit of meaning. Meaning emerges at the level of patterns, distributions, and constraints. The universe is not telling a single, deterministic story. It is generating statistically lawful ensembles. This is a different conception of order, one that does not require certainty in every instance. This also changes the role of explanation. To explain a quantum phenomenon is not to predict a single outcome with certainty, but to account for the structure of possible outcomes and their probabilities. Explanation becomes relational rather than narrative. It focuses on what is allowed, what is forbidden, and how often each allowed event occurs. The hidden discreteness beneath randomness also places limits on human control. Even with perfect experimental setup, some outcomes remain unpredictable. This is not because of experimental imperfections, but because unpredictability is part of how the universe operates. Yet this unpredictability is tightly bounded. The universe is unpredictable, but not unruly. The work initiated by Max Planck made this clear for the first time. By introducing the quantum, he revealed that apparent chaos was not a breakdown of law, but evidence of a different kind of law. His insight showed that randomness and order are not opposites. Randomness can be the expression of order operating at a level inaccessible to direct perception. This understanding also dissolves a common misconception that quantum theory implies a fundamentally irrational universe. In reality, the quantum universe is constrained more tightly than the classical one. Many outcomes that classical physics would allow are simply impossible in the quantum world. Electrons cannot spiral into atomic nuclei. Atoms cannot emit arbitrary frequencies of light. Chemical bonds have fixed strengths. Stability itself is a product of quantization. The randomness that remains is not chaos without structure, but freedom within boundaries. It is the freedom of timing, not of possibility. Nature chooses when an event occurs, but not how much energy it releases or which states are allowed. This balance between rigidity and unpredictability is one of the most distinctive features of quantum reality. Understanding this balance helps resolve the apparent paradox of order emerging from randomness. Order does not require predictability at the smallest scale, it requires constraint. Once constraints are in place, large-scale regularities become inevitable, even if individual events remain uncertain. The third keynote thus captures a subtle but transformative idea. The universe is not divided into order and chaos as opposing domains. Instead, chaos is often the visible expression of hidden order, and randomness is often the consequence of discreteness operating beyond intuitive reach. What appears noisy and unpredictable may be governed by rules stricter than anything classical physics imagined. This realization reshapes how humans interpret uncertainty in all contexts. It cautions against equating unpredictability with meaninglessness. It invites patience with complexity and humility toward intuition. The universe may be deeply ordered even when it refuses to behave in ways that feel orderly to us. In recognizing discreteness beneath apparent randomness, physics did not abandon the search for order. It refined it. It learned to look for order not in smooth trajectories and exact predictions of single events, but in constraints, distributions, and statistical laws. This shift did not weaken science. It strengthened it, allowing it to describe a reality that is both unpredictable and profoundly structured at the same time. As this understanding deepened, physicists began to see that the hidden discreteness beneath apparent randomness was not an isolated feature of a few exotic experiments, but a universal principle shaping the entire microscopic world. Wherever they looked, atoms, radiation, chemical reactions, the same pattern repeated itself. Individual events behaved unpredictably, yet the collective behavior obeyed laws of remarkable precision. This consistency forced a reconsideration of what random truly meant. In classical thinking, randomness implied a lack of explanation. If outcomes varied, the cause was assumed to be missing information or uncontrolled variables. But quantum phenomena resisted this interpretation. Even when experimental conditions were controlled with extraordinary care, outcomes still fluctuated. Two atoms prepared in identical ways could behave differently. The variation was not noise to be eliminated, it was part of the phenomenon itself. What made this especially striking was that the variability followed strict statistical rules. The probability distributions were stable and reproducible. They did not drift over time or depend on the mood of the experimenter. This stability revealed that randomness itself was regulated. Nature was not improvising freely. It was operating within a tightly constrained framework. Discreteness was the key to this regulation. Because physical quantities existed only in fixed units, the range of possible outcomes was sharply limited. This limitation acted like a hidden scaffolding beneath the apparent chaos. Events could occur at unpredictable times or in unpredictable sequences, but they could not violate the underlying quantum structure. In this sense, discreteness functioned as a form of invisible discipline. This realization transformed how scientists interpreted fluctuations. Instead of treating them as errors or imperfections, fluctuations became sources of information. The pattern of randomness itself revealed the underlying rules. By studying statistical distributions, physicists could infer the structure of energy levels, transition probabilities, and interaction strengths. Noise became a signal. The concept of hidden discreteness also explained why attempts to force classical continuity onto microscopic systems consistently failed. Classical models allowed infinitely fine variations, but experiments repeatedly showed sharp boundaries. Systems jumped between states instead of sliding smoothly. Whenever classical theory predicted a continuous spread, nature responded with discrete lines or thresholds. The universe was enforcing its own accounting system. This enforcement had profound consequences for stability. Atoms, for example, are stable precisely because electrons are restricted to discrete energy levels. Without quantization, electrons would radiate energy continuously and collapse into the nucleus. Matter as we know it would not exist. What appears to be static, solid order at the macroscopic level depends entirely on microscopic jumps and restrictions that look random when viewed individually. The same principle applies to chemical behavior. Chemical reactions occur through discrete changes in bonding configurations. Reaction rates fluctuate, but the possible outcomes are limited by quantized energy states. This is why chemistry is reliable despite being rooted in probabilistic events. The discreteness of underlying processes ensures consistency at larger scales. As physicists embraced this view, randomness lost its association with chaos and meaninglessness. Instead, it became a sign that observation was occurring at a level where individual events mattered. Randomness indicated proximity to the fundamental scale of reality. At that scale, certainty dissolves, but structure remains. This also clarified why human intuition struggles with quantum phenomena. Human perception evolved in a world where enormous numbers of quantum events are averaged together. Smoothness, continuity, and predictability are emergent properties of large systems. At small scales, where averaging no longer applies, intuition breaks down. What feels chaotic is simply unaveraged reality. The hidden discreteness beneath randomness also reshaped the scientific method. Prediction was no longer about forecasting exact outcomes, but about predicting distributions. Experiments were judged successful not by whether they produced identical results each time, but by whether their statistical patterns matched theoretical expectations. Agreement meant alignment of probabilities, not replication of individual events. This shift required a new form of rigor. Statistical predictions had to be precise. Small deviations in distributions mattered deeply. Quantum theory proved itself not by eliminating randomness, but by explaining its structure. The theory succeeded because it told scientists exactly how unpredictable systems should behave on average. The philosophical implications were unavoidable. The idea that reality is fundamentally deterministic had to be reconsidered. Determinism, once seen as the hallmark of scientific explanation, became optional rather than essential. Order no longer required certainty in every instance. It required reliability in patterns. This did not imply that reality was arbitrary or subjective. On the contrary, the constraints imposed by quantization were universal. They applied everywhere, regardless of observer or context. The randomness was objective, not dependent on human ignorance or choice. This marked a profound shift in how objectivity itself was understood. The work initiated by Max Planck thus revealed a universe where unpredictability and structure coexist seamlessly. His introduction of the quantum showed that apparent disorder could be the surface manifestation of deeper regularities. This insight dismantled the classical opposition between order and chaos, replacing it with a layered view of reality. In this layered view, different descriptions apply at different scales. At the smallest scales, discreteness dominates and outcomes are probabilistic. At larger scales, averaging smooths out randomness, producing the continuous laws familiar from classical physics. Neither description is wrong, each is appropriate to its domain. Order is not destroyed by randomness, it emerges from it. This understanding also changed how scientists thought about limits. The limits imposed by quantization are not obstacles to knowledge, but guides. They indicate where certain questions lose meaning and where new kinds of questions become appropriate. Asking for exact trajectories at the quantum level is like asking for the precise position of a wave crest in a storm of countless ripples. The question assumes a structure that does not exist. Recognizing discreteness beneath randomness, therefore, involves letting go of certain expectations. It requires accepting that nature does not always provide answers in the form we prefer. It provides constraints, probabilities, and patterns instead. Understanding comes from aligning our questions with that structure. The third keynote ultimately reveals a universe that is neither chaotic nor rigidly predictable, but profoundly ordered in a non-classical way. Randomness is not the enemy of law, it is the visible expression of law operating under strict constraints. Discreteness is the silent architect shaping outcomes without announcing itself. By embracing this view, physics gained a deeper coherence. The apparent contradictions between randomness and order dissolved. What once looked like chaos became evidence of structure operating at a scale beyond direct perception. The universe was not less ordered than previously thought, it was more subtle. This insight continues to influence how humans understand complexity in general. It suggests that unpredictability does not imply absence of structure, and that stable patterns can emerge from systems governed by probabilistic rules. In recognizing discreteness beneath apparent randomness, science learned to see order where intuition once saw only noise. The third keynote, in its full depth, teaches that the universe does not owe us simplicity. It offers structure instead, sometimes hidden, sometimes indirect, but always present. What looks random may be the most honest expression of a deeper, stricter order quietly shaping reality from beneath the surface. The realization that probability could function not as a weakness of knowledge, but as a doorway to deeper order marked one of the most profound shifts in the history of science. For centuries, probability had been treated with suspicion in physics. It was tolerated as a practical tool, useful when systems were too complex to track in detail, but never regarded as fundamental. True understanding, it was believed, meant certainty. To know the laws of nature was to know exactly what would happen, given sufficient information. Anything less felt like failure. This attitude began to erode when classical explanations repeatedly collapsed at the microscopic scale. As quantum ideas took hold, it became increasingly clear that probability was not merely compensating for ignorance. It was doing explanatory work that determinism could not. Certain phenomena could be described accurately only in terms of likelihoods. Attempts to replace these likelihoods with hidden certainties failed again and again. The universe seemed to insist on speaking the language of probability. What made this unsettling was that probability appeared exactly where physicists most wanted precision. When dealing with atoms, radiation, and subatomic processes, outcomes could not be predicted individually, even in principle. Yet the statistical predictions were astonishingly accurate. The probabilities themselves obeyed strict laws. This paradox forced a redefinition of what order meant. Order was no longer tied to predictability of single events. It was tied to stability of distributions. A single atomic transition might occur unpredictably, but the pattern formed by millions of such transitions was rigid and reliable. The deeper order lay not in individual outcomes, but in the structure governing how often each outcome occurred. Probability was not masking order, it was revealing it. This shift required abandoning the idea that causality must be linear and complete. In classical physics, a cause was expected to determine a single effect. In the probabilistic framework, a cause defined a range of possible effects, each with a specific likelihood. This did not weaken causality, it generalized it. Causes no longer dictated exact futures, but shaped probability landscapes. The universe specified tendencies rather than certainties. Once this perspective was accepted, probability began to look less like a compromise and more like a principle. It allowed physicists to describe systems whose internal details were not only unknown, but unknowable in the classical sense. Probability became the bridge between microscopic discreteness and macroscopic regularity. It explained how stable laws could emerge from unpredictable events. The role of probability also clarified why chaos and order coexist so naturally in quantum phenomena. Randomness at the level of individual events does not accumulate into disorder because the probabilities themselves are structured. Each event samples from the same underlying distribution. Over time, these samples average out, producing consistent results. The order resides in the distribution, not in the sequence. This insight transformed the interpretation of experimental data. Variability was no longer something to be eliminated at all costs. Instead, it was something to be measured carefully. The shape of fluctuations, their frequency and spread, carried essential information. Probability distributions became fingerprints of underlying physical laws. The deeper order revealed by probability is subtle because it resists visualization. Human intuition prefers concrete narratives. This happened because that happened. Probability replaces narrative with structure. It tells us not what will happen, but what can happen and how often. This requires a different kind of understanding, one less attached to certainty and more attuned to pattern. The intellectual courage to accept this shift traces back to the foundations laid by Max Planck. Although he himself was uneasy with the philosophical consequences, his work opened the door to a world where probability was no longer optional. Once energy was quantized, uncertainty in outcomes became unavoidable. Probability was not introduced to soften the theory, it emerged because reality demanded it. This probabilistic order also imposed limits on human ambition. It showed that some questions are not just difficult, but ill-posed. Asking for the exact time of a specific atomic decay is not like asking for the time of sunrise tomorrow. The universe does not contain that information in a deterministic form. What it contains is a probability. Understanding means respecting that boundary. Yet this limitation is paired with extraordinary power. Probabilistic laws allow astonishingly precise predictions at large scales. Technologies built on quantum principles work because probabilities are reliable. Lasers, semiconductors, and countless modern devices depend on statistical regularities that never fail. The success of these technologies is practical proof that probability reveals genuine order. This reframing also dissolves the false opposition between objectivity and uncertainty. Probabilities in physics are not expressions of personal belief or subjective doubt. They are objective features of the world. Different observers, using the same conditions, will assign the same probabilities. The uncertainty lies in outcomes, not in the laws describing them. By accepting probability as fundamental, physics gained a deeper coherence. Instead of forcing reality into deterministic molds, it allowed the structure of reality to dictate the form of explanation. Order was no longer something imposed by theory, it was something uncovered by listening to how nature behaved. The fourth keynote, when fully understood, shows that probability is not the enemy of meaning, it is a refined expression of it. It allows a universe that is flexible without being arbitrary, unpredictable without being chaotic, and constrained without being rigid. Probability is the doorway through which deeper order becomes visible, not despite uncertainty, but because of it. The idea that chaos reveals structure, instead of destroying it, represents one of the most counterintuitive insights to emerge from modern physics. For much of human history, chaos was treated as the enemy of understanding. Disorder implied breakdown, failure, or absence of law. When systems behaved unpredictably, it was assumed that explanation had reached its limit. Science, in this view, was the gradual conquest of chaos, replacing confusion with certainty and randomness with order. Yet the deeper exploration of physical reality overturned this assumption. Chaos did not mark the end of structure, it often marked the place where structure became more sophisticated than intuition could immediately grasp. Instead of erasing order, chaos exposed the inadequacy of simple models and forced the discovery of deeper organizing principles. In the transition from classical to quantum physics, this lesson became unavoidable. Phenomena that appeared chaotic at first glance, irregular radiation patterns, unpredictable atomic events, fluctuating energy exchanges, turned out to be governed by rigid constraints. The apparent disorder was not the absence of law, but the presence of law operating at a level that resisted straightforward visualization. This shift required a redefinition of what structure looks like. Classical structure was linear, smooth, and directly observable. It relied on continuity and determinism. Quantum structure, by contrast, was discrete, statistical, and indirect. It did not announce itself through neat trajectories or predictable sequences. Instead, it revealed itself through patterns that emerged only when many events were considered together. Chaos played a crucial role in this revelation. When classical equations failed dramatically, producing infinities, contradictions, or nonsensical predictions, it became clear that the apparent chaos was not in nature, but in the mismatch between theory and reality. The failure of familiar structures forced physicists to look for new ones. Chaos became a diagnostic tool, highlighting exactly where assumptions broke down. Once these assumptions were questioned, structure reappeared in unexpected places. Instead of smooth curves, there were discrete levels. Instead of exact predictions of individual events, there were precise probability distributions. Instead of continuous flows, there were jumps governed by strict rules. Chaos had not destroyed order, it had stripped away a false image of order and revealed a more accurate one underneath. This dynamic shows that chaos is often relational rather than absolute. A system appears chaotic only relative to a particular framework of understanding. When the framework changes, what looked like disorder can suddenly appear structured. The radiation spectrum was chaotic only from the perspective of classical continuity. From the quantum perspective, it was highly ordered. This insight extends beyond physics. In many complex systems, weather, ecosystems, economies, chaos does not imply lack of structure. It implies sensitivity to initial conditions and interaction across scales. The system follows rules, but small differences amplify, making precise prediction difficult. Yet within this unpredictability, stable patterns, cycles, and constraints persist. Chaos reveals which variables matter and which assumptions are fragile. In quantum theory, Chaos exposed the limits of determinism. It showed that demanding certainty at the level of individual events was misplaced. The structure of reality was not located in exact sequences, but in statistical regularities. Once this was accepted, the apparent chaos of microscopic behavior became intelligible rather than threatening. This change also transformed the scientific attitude toward anomalies. Instead of being dismissed as errors, anomalies became signals of deeper structure. The ultraviolet catastrophe was not an embarrassment to be hidden, it was a doorway to quantization. Each breakdown of classical order pointed toward a more fundamental organizing principle waiting to be discovered. The role of thinkers like Max Planck was crucial in this transformation. By taking chaos seriously instead of explaining it away, he demonstrated that disorder could be informative. His willingness to accept an idea that felt unnatural showed that structure does not always align with intuition. Sometimes structure is revealed only when intuition fails. Chaos also taught a lesson about scale. What appears chaotic at one level can be highly ordered at another. Individual quantum events are unpredictable, but large-scale behavior is extraordinarily stable. This layered order means that chaos and structure are not opposites. They are complementary descriptions at different resolutions. The universe is not chaotic or ordered in an absolute sense. It is both, depending on how closely one looks. This understanding dissolves the fear that accepting chaos undermines meaning. On the contrary, it expands meaning. It shows that order does not have to be rigid or simple to be real. Complex, probabilistic, and indirect forms of order can be just as lawful as classical determinism, sometimes even more so. The recognition that chaos reveals structure also imposes humility. It warns against confusing familiarity with truth. Structures that feel intuitive may fail under new conditions, while unfamiliar structures may succeed spectacularly. The task of understanding is not to force reality into comfortable patterns, but to remain open to patterns that emerge when old ones collapse. In this sense, chaos becomes a creative force in knowledge. It destabilizes assumptions, exposes hidden limits, and compels deeper inquiry. Without chaos, false structures can persist unchallenged. With chaos, those structures are tested and either refined or replaced. Progress depends on this tension. The fifth keynote ultimately teaches that chaos is not the destruction of order, but its transformation. When systems appear chaotic, they are often inviting a shift in perspective. They are asking for new concepts, new scales, and new forms of explanation. What looks like disorder may be the visible trace of a deeper, more subtle structure asserting itself. Understanding this changes how one relates to uncertainty. Instead of resisting it, one learns to interrogate it. Instead of fearing disorder, one looks for the constraints shaping it. Chaos becomes not an endpoint, but a beginning, the moment where hidden structure starts to come into view. The recognition that human intuition has limits, and that science advances most decisively when it acknowledges those limits, stands as one of the quiet but profound lessons of modern physics. For a long time, intuition was treated as an ally of truth. Theories that aligned with everyday experience felt trustworthy, while ideas that violated common sense were met with suspicion. This approach worked well as long as science remained within the scale of direct human perception. Motion, force, heat, and light behaved in ways that roughly matched lived experience. But as inquiry pushed beyond the familiar, intuition began to fail, not gradually, but dramatically. The breakdown did not occur because human reasoning is weak, but because it evolved to navigate a specific environment. Intuition is shaped by survival at macroscopic scales, where objects are solid, time flows smoothly, and causes appear to produce immediate, continuous effects. At the microscopic level, these assumptions lose relevance. The universe does not become irrational, it simply stops catering to the expectations formed by human experience. The quantum revolution made this failure of intuition impossible to ignore. Phenomena emerged that could not be pictured in familiar terms. Particles behaved like waves, waves behaved like particles, and outcomes could not be predicted with certainty, even when conditions were carefully controlled. Attempts to force these phenomena into classical mental images produced paradoxes rather than clarity. The discomfort this caused was not a flaw in the theory, but a signal that intuition was being asked to operate outside its domain. One of the most humbling aspects of this shift was the realization that mathematical consistency could outrank visualizability. A theory could be deeply counterintuitive and yet precisely correct. This reversed a long-standing hierarchy in scientific thought, where intuitive plausibility often guided acceptance. In the new framework, the question was not whether a theory felt right, but whether it worked reliably and coherently. This shift demanded intellectual humility. It required scientists to admit that understanding does not always mean being able to picture a process unfolding step by step. Sometimes understanding means accepting abstract rules that resist visualization but produce accurate predictions. The desire for a complete mental image had to be set aside in favor of structural coherence. The limits of intuition also reshaped how explanation itself was defined. Classical explanations relied on continuous narratives: this object moves, collides, transfers energy, and causes that outcome. Quantum explanations often lack such narratives. They specify conditions, constraints, and probabilities rather than sequences of events. This can feel unsatisfying, but it reflects the nature of the phenomena being described. The humility imposed by this realization was not merely personal, it was methodological. It encouraged caution in extending familiar concepts beyond their tested range. It taught that success at one scale does not guarantee validity at another. The universe is layered, and each layer may require its own language. This humility also protected science from dogmatism. When intuition is treated as absolute, theories become rigid. Anomalies are dismissed rather than explored. By recognizing the limits of intuition, physicists became more willing to let evidence reshape their conceptual frameworks. The refusal to cling to comforting pictures opened the door to deeper insights. The work of pioneers such as Max Planck exemplifies this humility. Although he personally preferred deterministic explanations, he accepted an idea that violated his intuition because it resolved contradictions and aligned with observation. This willingness to prioritize coherence over comfort was not a rejection of reason, but a refinement of it. The limits of intuition also clarify why debates about interpretation persist. When phenomena cannot be directly visualized, multiple conceptual stories can coexist, each mapping abstract rules onto different metaphors. These debates are not signs of weakness in the theory, but reflections of the difficulty of translating non-intuitive structures into human language. Acknowledging the limits of intuition does not diminish human understanding. It expands it. It allows science to operate beyond the boundaries of everyday experience, guided by consistency, evidence, and predictive power rather than by familiarity. This expansion comes at the cost of comfort, but with the reward of deeper accuracy. There is also a moral dimension to this humility. It reminds humans that they are participants in the universe, not its measure. Reality is not obligated to be simple, visible, or intuitively satisfying. The role of science is not to domesticate nature into human categories, but to adapt human categories to nature's structure. This lesson resonates beyond physics. In any complex system, biological, social, or psychological, intuition can mislead. Patterns that feel obvious may be superficial, while underlying dynamics remain hidden. Recognizing the limits of intuition encourages patience, openness, and respect for complexity. The sixth keynote ultimately teaches that progress in understanding often begins with surrender. Surrender of the demand that reality conform to familiar images, and surrender of the belief that human intuition is a universal guide. In making this surrender, science does not lose clarity, it gains it. Humility, in this sense, is not weakness. It is a disciplined recognition of scale, context, and limitation. It allows knowledge to grow without becoming dogmatic. By accepting that intuition has boundaries, physics found the freedom to describe a universe far richer and more precise than intuition alone could ever imagine. The final keynote draws together all the previous insights into a broader reflection on meaning, order, and human responsibility in a quantum world. Once the universe is understood not as a perfectly predictable machine, but as a layered reality governed by constraints, probabilities, and limits, the question of meaning can no longer be framed in purely deterministic terms. Meaning does not disappear with certainty, it changes form. Classical physics encouraged a worldview in which meaning was closely tied to predictability. If the universe unfolded according to fixed trajectories from precise initial conditions, then understanding meant control. To know the laws was, at least in principle, to foresee outcomes and to dominate uncertainty. Human responsibility in such a world was framed around mastery, improved measurement, refined calculation, and the future becomes transparent. The quantum view quietly dissolves this fantasy. It does not present a universe without order, but a universe where order does not guarantee control. The laws are exact, yet they do not specify single outcomes in every case. Instead, they define boundaries within which events occur. Possibility replaces certainty, and probability replaces inevitability. This shift has deep implications for how humans understand their place in reality. Meaning in a quantum world is not located in perfect foresight. It is located in structure, limits, and participation. Humans are not external observers standing outside a clockwork universe. They are embedded within processes whose outcomes are partly open. This openness is not chaos, it is a disciplined openness governed by law. The universe allows variation, but only within strict constraints. This has an ethical dimension. When outcomes are not fully predetermined, responsibility cannot be reduced to mechanical causation. Choices matter, not because they override physical law, but because they operate within a landscape of real alternatives. The quantum world is not a realm of unlimited freedom, but neither is it one of absolute necessity. It is a world where constraints and possibilities coexist. The recognition that certainty has limits also reshapes humility. Humans cannot claim complete knowledge or total control, even in principle. There are boundaries beyond which prediction becomes meaningless, not due to ignorance, but due to how reality itself is structured. Accepting these boundaries is not a defeat of reason. It is an alignment with reality. This alignment changes how progress is understood. Progress is no longer measured solely by the elimination of uncertainty. Instead, it is measured by how well uncertainty is understood, respected, and integrated into coherent frameworks. The success of quantum theory lies not in removing unpredictability, but in explaining its structure so precisely that reliable knowledge becomes possible despite it. The quantum world also reframes the relationship between humans and nature. Nature is not a passive system waiting to be decoded completely. It is an active participant in every interaction. Measurement itself becomes a process with consequences. This does not mean that reality is subjective, but it does mean that knowledge is relational. What can be known depends on how inquiry is framed. This relational aspect carries responsibility. How questions are asked matters. What is chosen to be measured and what is ignored shapes the knowledge produced. In a world where not all questions have deterministic answers, wisdom lies in asking the right questions rather than demanding impossible ones. Meaning, then, is not weakened by uncertainty. It is deepened. A universe that is entirely predetermined leaves little room for significance beyond mechanics. A universe that is structured yet open allows for emergence, novelty, and genuine consequence. Quantum order permits surprise without abandoning law. The legacy of figures such as Max Planck illustrates this balance. His work did not abolish order, it revealed a stricter and more subtle one. In doing so, it placed new demands on human understanding. Precision became more important than intuition, humility more important than certainty, and coherence more important than comfort. This worldview also influences how humans approach complexity beyond physics. In social systems, ecosystems, and even personal lives, outcomes are rarely fully predictable. Yet they are not arbitrary. They are shaped by constraints, feedback loops, and probabilities. The quantum lesson cautions against both fatalism and overconfidence. It suggests that while not everything can be controlled, much can be understood in terms of structure and tendency. Responsibility in such a world lies in working with constraints rather than denying them. It lies in respecting limits, recognizing patterns, and making decisions informed by probabilities rather than fantasies of certainty. This is a more mature form of responsibility, one that accepts risk without surrendering to chaos. The quantum perspective also challenges simplistic notions of meaning that rely on absolute predictability. Meaning does not require a fully scripted universe. It requires coherence, consistency, and the possibility that actions make a difference within real bounds. The presence of probability does not erase purpose, it situates purpose within a structured openness. In this sense, the quantum world is neither cold nor nihilistic. It is disciplined and generous at the same time. It enforces rules, but it allows variation. It limits what can happen, but it does not dictate every detail. This balance creates space for complexity, creativity, and responsibility. The seventh keynote ultimately points toward a redefinition of what it means to understand reality. Understanding is not possession of certainty, but alignment with structure. It is the ability to navigate a world that is lawful without being fully predictable. It is the recognition that limits are not failures, but features. In accepting this, science does not abandon meaning, it refines it. Meaning becomes something that emerges from engagement with a universe that is ordered, constrained, and open all at once. The quantum world does not undermine significance, it demands a deeper, more honest account of it, one grounded in humility, responsibility, and respect for the subtle order that governs even the most uncertain phenomena.